Right, we are back, and do I have an answer? Which is better while working with ultra short pulses? Is KDP better or is lithium niobate better? KDP is better, because see, the problem is this. What it means is that if delta nu is more than 20 centimeter inverse, you will not get second harmonic generation for KDP. But if delta nu is more than 0.5 centimeter inverse, you will not get second harmonic generation for lithium niobate. And we know very well that the characteristic of an ultra short pulse is a large bandwidth. Shorter the pulse, bigger the bandwidth, right. So, if you are going to use a short pulse, femtosecond pulse, and use lithium niobate to generate second harmonic wavelength, what will happen? Your modal wavelength is 1064 nanometer for fundamental. So, you are going to generate 532 nanometer, fine, but the bandwidth will be very small. Yes, if bandwidth is very small, then we have studied transform limited pulses. If bandwidth is small, then what does that mean? What does that, how does that affect the pulse width? Pulse width becomes large, right. Remember, the delta nu multiplied by delta t, that would be a constant depending on what shape the pulse is. And the physical reason for that is, if the spectral bandwidth is large, that means a large number of longitudinal modes have been locked to produce the pulse. Greater the number of modes locked, shorter is the pulse, wider is the spectrum. So, now after second harmonic generation, if the spectrum has become narrow just because your delta nu is small for the crystal, then automatically what will mean is that in the second harmonic light, very small number of modes are locked, right. Bandwidth is small, that means fewer number of modes would be locked compared to fundamental, which would mean that the pulse width would be significantly larger compared to the fundamental, right. Even 20 centimeter inverse is not very large, but at least it is much better than 0.5 centimeter inverse. So, you want a crystal. So, that is the first point we want to make here. You want a crystal for which delta nu is going to be large, as large as possible, so that your pulse does not become temporally broadened. Spectrally it will become narrower, but at the same time temporarily it will become broader if delta nu is small. So, in order to ensure that your ultra short pulse remain ultra short even after frequency doubling, you want delta nu to be as large as possible, right. And what determines delta nu? The material. So, this is an important point here. You want to use a material for which delta nu is large, okay, while working with ultra short pulses. Okay. So, it is a very complicated thing. First of all, you want a large value of second order nonlinear susceptibility, right, chi second order. Then you want the crystal to be birefringent. Then when you are working with ultra short laser, you want the delta nu to be large as well. So, we are getting into more and more restrictions, and in fact, there will be one more before we complete this discussion. So far, we have talked about this bandwidth business. Next, we want to discuss another aspect of ultra short pulses, and that is group delay. We will say what group delay is, but the central theme of this entire discussion is something that we had discussed several modules earlier. The issue is our ultra short laser is not a single mode laser. Lot of longitudinal modes are actually locked to produce the ultra short pulse. Okay. So, whatever discussion we had earlier during mode locking, that becomes the determinant in the discussion we are going to perform now. So, when we do the experiment, we do not even think, we tweak this, we tweak that and things happen. But a lot of effort by many people has gone into the system before we could use it as a toy. And it is important that we understand, we do not need to know all the math, but we should at least understand the principles. Otherwise, if we have to design experiment, if we do not know these, we will end up taking out a crystal from anywhere and trying to do second harmonic with ultra short pulse, and it will not work. Okay. So, second factor, group delay. Now, see, we have discussed earlier that plane waves are characterized by their phase velocity, right. Vph equal to omega by k is equal to c divided by refractive index at that value of omega. We have talked about this earlier. Yes. So, now how do I define pulsed light? Pulsed light, you said, is actually not used, you did not say anything, I said, but you know that pulsed light is a mixture of many plane waves, right. So, the amplitude, the wave function of pulsed light can be written like this. Okay, you might as well write a summation if we write an integration, because it is easier to arrive at the next step if you do an integration. You can do it numerically as well. Okay. So, let us understand what we have written. Forget about this integral for the moment, we will come to that. What is this? A at k multiplied by e to the power I k z by minus omega t. That is the expression of a plane wave, we have written that, right. And our ultra short pulse comprises of many such plane waves. So, what we are doing is, we are adding up all the fields. So, psi, as you know, is an amplitude and it depends on z as well as t. What is z? Z is the direction of propagation of light. Okay. If light goes in this direction, then this is z, direction of propagation of light, and of course, it is dependent on time as well. So, what we have is psi at some value of z and some value of t is an integral of this field for a plane wave over the entire range of plane waves. So, integral dk and lower limit is k 0 minus delta k, upper limit is k 0 plus delta k. So, what is k 0? K 0 is the k value of the modal, k 0 is the let us just say k 0 is the modal k value. So, delta k on this side, delta k on that side, we are working with a symmetric kind of distribution. Okay. How do you do it? We are not going to do the entire integration, any integration enthusiast is welcome to do so. I will just tell you how it starts and I will show you what the final answer is. So, to work out this integral, what is done is omega. So, as we said earlier, every plane wave is characterized by a k vector and an omega, right, a characteristic k vector, characteristic omega. So, we can pretend as if omega is a characteristic of k. So, we can write omega for a particular k value, that is written as omega 0, again the modal omega, plus d omega dk 0 multiplied by k minus k 0. Does this ring a bell? Have you encountered an expression like this somewhere in spectroscopy, fundamental spectroscopy, not in this course? Yeah, where? And a little louder please. Very easy question. As demonstrated many times, I do not ask difficult questions. Yeah, where have you encountered? Why Raman? What about vibration? When you derive the vibration selection rule, how do you write the dipole moment? Mu equal to mu 0 plus del mu del x multiplied by x. So, that is what it is. Okay. This is the rate of change of omega with respect to k, that is multiplied by k minus k 0. It works because k minus k 0 is a small quantity. Okay. This is how it is expanded, and then after doing the integration, now I will show you the final expression. Please do not get scared. We will demonstrate that it is not very difficult expression. So, this is the final answer, nothing to be scared of, as you will see. Psi at z and t, particular value of z, particular value of t, turns out to be 2 a at k 0. A at k 0 means amplitude for the modal k value k 0. Neglect this thing for the moment. The last factor is e to the power I k 0 z minus omega 0 t. That is quite simple, is not it? What is e to the power I k 0 z minus omega 0 t? That is the same expression you have here. Instead of z you have written, instead of k you have written k 0, instead of omega you have written omega 0. So, that is the expression for the once again the plane wave at the center of the distribution, all right. I am talking about this one. I wish I had better control over my fingers, but I do not, all right. This is what I am saying. So, do you see that that is what comes from the plane wave at the center of the distribution, and this okay, it is the amplitude, it comes from the integration. What are we left with? What are we left with here? What kind of a function is that? Earlier we had sin square theta by theta. Is it that or is it something else? It's sin theta by theta. So, what is the difference between sin square theta by theta square and sin theta by theta? More or less similar looking functions, but there is a difference, yes. Sin square theta by theta square is always positive, but this goes negative, it is not too much negative, but it does go negative. So, this is the shape. Okay. Now, this whole thing here is the amplitude of the wave packet. Let the term wave packet not scare you. Some people write wave packet as one word, some people in some books, most of the books wave packet is written as 2 words. I prefer to write these things as one word always. Nanoparticle is one word for me, wave packet is one word for me, because I am influenced by a television series that I saw as a kid that was on bodyline bowling. You know bodyline? Douglas Jardine, Don Bradman. So, there was this scene where this British reporter is trying to send a message by telegram, and he fights with the clerk at the telegraph office, because he wrote bodyline, which was a new word at that time, there was no such word earlier. So, the clerk insisted that this is 2 words. So, every time you write bodyline you have to pay for 2 words, and the journalist insisted that no, it is a new word, it is one word. So, somehow that got into my head, and I like to combine words whenever I can. So, for me wave packet is one word, you write whatever you want. What is the meaning of wave packet? What is a wave packet? My favorite answer to this question sounds almost stupid. A wave packet is a packet of waves. It sounds very strange, mundane, and but actually that is what it means. You combine a lot of waves, right, that gives you a packet of waves, and you combine them in such a way that at one particular point they are all in phase. Then as you go out on either side, they go out of phase, and that is why you get a shape like this. Okay. How do you generate a wave packet? We are going to discuss this later. Suppose once again it is related with that spectral bandwidth of ultrafast pulses, ultra short pulses. Suppose you excite something using an ultra short pulse. Excitation starts from V equal to 0 of the lowest of the ground electronic state, let us say, right. What is the destination? Can you say that we only populate say V equal to 3, V dash equal to 3 of S1? You cannot, because there is a distribution, right. Some molecules will be excited to V dash equal to 3, some might be excited to V dash equal to 2, some will be excited to V dash equal to 4, and so on and so forth. And then that will form a coherent wave packet. And coherent wave packet dynamics is an important problem that has been studied for ages in ultrafast spectroscopy. We are going to discuss it in this course as well. But for now, this is a wave packet, okay, ultra short pulse, and this is the shape that you get of the amplitude of the wave packet. Now, this entire wave packet is not stationary, it is not a standing wave, the entire wave packet moves, okay, and it moves with what is called a group velocity given by d omega dk 0. Do you get the significance of d omega dk 0? Look at this function. Where will the function be equal to 0? Z equal to z minus d omega dk 0 t is equal to 0, right. That is where this is going to be equal to 0. Is that right? What is z by t? So, what we are saying essentially is that z equal to d omega dk 0 t. Okay. So, what is z by t? I cut t from here and I write t here. Z by t is equal to d omega dk 0. This. Why do you call that group velocity all of a sudden? What is z? What is z? Last letter in English alphabet? Yes, but in this context, what is z? You have to speak loudly. It is a big room, very few people are there. I cannot, I am a little short of hearing. Yeah? What is z? Z is the direction of propagation of light. So, what is z by t? Distance covered in direction of propagation of light per unit time, that is velocity, right. So, z by t essentially is the velocity with which this entire wave packet moves, okay, d omega dk 0. This is called a group velocity, not group delay yet, delay comes later. When we talk about delay, you have to talk about two kinds of light. The two kinds of light in this context are fundamental and second harmonic. We will come to that. For now, what we have been able to do is, we have been able to define group velocity of a wave packet. So, group velocity is d omega dk 0, okay. And just for the record, fundamental and second harmonic have different group velocities, and that creates another problem. One problem we have discussed already is delta nu. The other problem is that if fundamental and second harmonic travel with different group velocities, then this is the situation you get as time passes. They move away from each other. So, the question is, what is the difference in times taken by fundamental and second harmonic to travel the entire length of the crystal? Okay. Once again, without derivation, I will give you the expression, this is what it is. Delta t is given by 1 by c dnf d lambda f multiplied by lambda f, where f is fundamental, equal to dn sh d lambda sh multiplied by lambda sh. I might as well have, like the previous slide, I might as well have written dn d lambda, then put a bracket and written f as subscript. That would have perhaps been better. Okay. So, you do not want too much of delta t, that is the issue. They have to travel together for the wave packet to sustain. So, now what do you want? You want the delta t to be smaller than the laser pulse duration, yes. So, in other words, we can say that delta t should be almost equal to 0, time required. So, as long as they are within the crystal, they should be together, the fundamental and second harmonic. So, if delta t is to be equal to 0, work with this expression, equate that to 0, what do you get? Yes? While doing that, do not forget something. When you equate that to 0, is there some relationship between lambda f and lambda second harmonic? There better would be, What is the relationship? Yes, lambda f equal to 2 multiplied by lambda second harmonic. So, putting this expression into this, what do you get? You get something like this. Okay. This is another condition. dnd lambda of fundamental should multiplied by 2 should be equal to dnd lambda multiplied dnd lambda of second harmonic. dnd lambda, right, rate of change of refractive index with respect to wavelength for second harmonic should be equal to twice dnd lambda for fundamental. Okay. That is when your delta t is going to be 0, and delta t should be small in order to get good second harmonic generation using an ultra short pulse. Right. So, once again let me show you some typical values. Delta t for lithium niobate is 6, delta 3 for lithium iodate is 0.7, delta t for KDP is 0.08. So, which is the best out of these three from this point of view? Definitely KDP. Okay. So, the take home message from this module and the last one is that one needs to be careful about several things before one can think of doing second harmonic generation or some frequency generation of using ultra short pulses. First of all, you have to choose the right material, and there are so many parameters, right. We have said this once already. Large value of second order nonlinear susceptibility, birefringence, delta t has to be close to 0, and what else? What is the point we discussed just before this? Delta nu. Delta nu has to be as large as possible. Okay. One more thing that we have not really said explicitly, do you want to use a crystal that is very large, or do you want to use a crystal that is small? I mean, that is not too thick. Do you want to use a large path length within the crystal? Do you want to use a not so large path length? You want to use a thin crystal, because here you are talking about delta t. Delta t is going to be longer for a thicker crystal. See, delta t here is given in picosecond per centimeter, right. So, if you use too thick a crystal, first of all there will be dispersion. So, your pulse will become broad, and this delta t is also not going to help. So, these are several parameters that one needs to worry about when one wants to do nonlinear optical manipulations using your ultra short pulses, right. So, that brings us to the end of the discussion that we intended to do today, but let me just give you a preview of what we are going to discuss the next day. See, so far we have been talking about some frequency generation, right, combining two photons of small energies to produce a photon of larger energy, and that is easily understood. Is it possible to have a photon of large energy split into two photons of smaller energy in a nonlinear optical material? The answer is yes. It is just that it is a much more difficult process compared to some frequency generation, and that splitting into two kinds of light with smaller energy, longer wavelength, that has a name, and that name is parametric generation or optical parametric generation. Okay. So, it is really very small, like 1 in a million kind of probability, and the phenomenon is not easy to understand. So far, even though we did not do the derivations, we more or less understood what we are talking about, because we can think of real life analogies and all. Difference frequency generation is actually not easy to understand, because it deals with things like quantum entanglement. In fact, parametric generation is used to make what are called correlated photons or single photons or photon pairs, not of any use to us as such, but they have they are used in sophisticated optics experiments. We are not going to go into that in this course, but the point is it can happen. What we want to learn is, we are saying it is a 1 in a million kind of probability to get parametric generation. Is there any way to increase the intensity? So, now see what will happen. So far we were dealing with a situation where signal and idler meet at the nonlinear optical crystal and the pump is generated. In fact, when I say it like this, it sounds a little strange, is not it? Because when we say pump, we think the pump should go in. That is what is going to happen in parametric generation. So, the pump goes in and splits into signal and idler. So, signal and idler both have longer wavelengths, lesser energies. So, this is a good way of generating light of, so if using visible light, it is a good way of generating say IR light. Now, the question is, how do we get a higher intensity? Two ways. One is, do this parametric generation inside a resonator. So, if you have a parametric generator in say resonator means a laser cavity, right. If you do multiple reflections, then it happens multiple number of times, you are going to get some kind of increase in the output. The other way is to do what is called optical parametric amplification. That is what we use in our lab, right, and that is a 2-photon process. It is not only the pump that goes into the nonlinear optical crystal, it is pump and signal, and what you generate is signal and idler. Okay. That is what we are going to discuss next day. So, I think next module is going to be very, very sketchy principle of optical parametric generation and optical parametric amplification. We might not talk too much about optical parametric oscillation, and module after that will be a discussion of our TOPAS manual. What is there inside the optical parametric amplifier that we have? How does it work? Those of you who have worked with TOPAS, can you tell me what are the different kinds of light that are there inside? There are several crystals, isn't it? And what do? You do second harmonic generation in some crystals, you do something else in some other crystals. What is that? Don't you generate white light? So, that white light, now by angle tuning and all, one particular frequency from that white light, well, of course, it is modal frequency, that gets amplified. That is how an optical parametric amplification works. So, that is what we are going to sort of learn in the next couple of days, and we will perhaps say a few words about. So far, we are talking about collinear geometry. In fact, even our TOPAS has collinear geometry, but there are certain advantages that come if you use non-collinear geometry. And in context of optical parametric amplification, that instrument is called a NOPA, nonlinear optical parametric amplifier. So, if possible, in the next couple of modules or in the next 3 modules, this is what we are going to cover. Let us see whether we can give you some brief idea, sketchy idea about NOPA as well. Okay. Today we stop here.